All right, we'll go ahead and start chapter 4, which is on quadratic functions and equations. Before we actually get into some more intense polynomials, quadratic functions are always a good place to start because all the skills that we learn from quadratic functions will be able to be applied, anywhere, pretty much anywhere else. So that's why we're going to start here. So let's go ahead and let's define what a quadratic function is. So a quadratic function is any function of the form ax squared plus bx plus c, where a, b, and c are real numbers and a is not 0. So I know it's kind of janky up here going to the next line, so I'll just write it up here too. Plus c. That's the form that we're talking about. This form is known as the standard form. Now, the reason why a has to be non-zero is that if a is 0, then if a is 0, then that. Oops, I accidentally erased it. There we go. Now the reason why a has to be 0, a cannot be 0, is that if it is 0, then that, well, of course, anything times 0 is just 0, so that essentially goes away. And then I'm just left with bx plus c, which is a linear function. So in order for it to be a quadratic function, a has to be not a non-zero number. Okay. Now, when we graph quadratic functions, it forms a shape called a parabola. And regardless of the parabola that you draw, there are really two forms, well, technically 3, but we'll cover 2 here. There are 2 forms for the quadratic function. There's standard form, and there's what it's called vertex form. And the vertex form is given by this, where a, h, and k are real numbers. And the reason why it's called vertex form is that the point hk is the vertex of your parabola. So in this particular section, we're going to graph and find equations of quadratic functions in vertex form and standard form. There are essentially 3 ways we can graph quadratic functions. We can either graph it point by point, which is very tedious and I'm not going to really have time to get into. We can use the parts of the parabola to graph it, or we can use function transformations. Now, especially with function transformations, it can be it actually makes sense, especially when we talk about vertex form, because right here, that minus h, that's your horizontal translation. Your plus k is your vertical translation, and the a covers both reflection, y-axis, x-axis reflections, and vertical dilations. But we'll get more into that later. But for now, we'll go ahead and talk about the different parts of a parabola for a quadratic function, so that we can go ahead and graph it. And we'll start by doing this in vertex form, and then later on we'll get to how it relates to standard form. All right, so go. All right, so the first thing that we need to graph a quadratic function is what's called the axis of symmetry. Axis of symmetry of a quadratic function, which is denoted by the vertical line x equals h, is the vertical line which splits the parabola into 2 equal halves, which are reflections of each other. If you scroll down towards your notes, you'll see a picture of the parent function x squared, and you can see that the axis of symmetry completely splits that parabola right down the middle, where both sides are actually end up being reflections of each other across that axis. Then you also need the vertex. So the vertex of a quadratic function, which is h and k, h is the x value, k is the y value, is the point at which the behavior of the function changes either from increasing to decreasing or from increasing to decreasing. And this point also intersects with the axis of symmetry. And if you really look at both of these, it makes sense because the x value of your vertex is h, which is also the value of that vertical line x equals h. So if you're working problems where you're trying to use these parts to graph a quadratic function, once you know what your axis of symmetry is, you're already halfway there with the vertex. You just need to find the y value. The vertex not only determines where the axis of symmetry is, it also determines where your highest or lowest point of the quadratic function is. And that's determined by the value of a. So again, I mentioned that a cannot be 0, but it can be less than or greater than 0. So if a is greater than 0, meaning that if a is positive, then the y value of the vertex is the minimum value of the function. I mean, just take a look at the parent function below of x squared. A is positive because a is 1, and also that point is at the very bottom of the graph. So that's your minimum value. And on the other hand, if a is negative, then that makes the y value of the vertex the maximum value. Okay, because again, and again, we're talking specifically about the y value of the vertex. The x value of the vertex only tells you where the maximum and minimum value are and where the axis of symmetry is. It's the y value of the vertex that's the actual minimum or maximum value. Other than the axis of symmetry in the vertex, the only other thing that we need in order to graph quadratic functions is the y-intercept. In other words, the point where the function crosses the x-axis, and of course, that's the point where x equals 0. Okay, let's look at an example. Let's see. Bring this over here. All right, so here's my quadratic function. 3 times, so f of x equals 3 times x minus 4 squared minus 2. Okay. So I want to know what my axis of symmetry is. I want to know what my vertex is. And I want to know what my y-intercept is. So first things first, axis of symmetry. So again, this is in the form a times x minus h squared plus k. Now, again, because of the nature of the function transformation, the horizontal translation, x minus h is the correct form. So whatever's here, whatever's in this spot right here, especially if that's a minus, that's going to be positive. So remember when we did horizontal translations, we have to think opposite. X minus means we're going to the right, which is a positive direction, so the x value is positive. X plus is going in the left, going to the left, which is a negative direction. So the x value would be negative. So here, my axis of symmetry is going to be a positive number, x equals 4. And of course, that's also the x value of the vertex. To find the y value, well, that's pretty easy. That's this. And again, like vertical translations, it's pretty straightforward. Plus k means your y value is positive. Minus k means your y value is negative. So here, -2 is the y value of my vertex. Now we need to find the y-intercept. Again, that's the place where the value of x is 0. So I just need to find the y value for when x is 0. So I'm going to take that 0 and substitute it in this problem. So f of 0 is 3 times 0 minus 4 squared minus 2. All right, so that's 0 minus 4 is -4. This is 16. That's 48 minus 2, which is 46. So my y-intercept is the point 0, 46. Okay. So let's go ahead and put this to a graph. I'm going to go ahead and switch over to Desmos so you can see it. All right. So again, we're keeping in mind that our axis of symmetry is x equals 4. Our vertex is 4, -2. My y-intercept is 0, 46. Okay, so I am going to have to change the the graph on this one. So let's see. Let's go with -10 to -50, or positive 50, I should say. All right, that's enough. Okay, so let's see. So x equals 2. I'm sorry, x equals 4 is my axis of symmetry. Now you don't have to draw the axis of symmetry, but it helps to do so. 4, -2 is my vertex, which is about right here. This is 4. Oh, sorry, wrong one. Each tick mark is 2, so it's actually right here. All right, then. So my y-intercept is 0, 46, which is about 2, 4, 6 right here. So now I'm going to go ahead and connect these dots right here. Let me try again. Yeah, there we go. It's about as close as I'm going to get to it. Now, how do I graph the other side? Because that's only just one side. Well, again, this axis is supposed to reflect this on that side. So looking at this, my y-intercept is 1, 2, 3, 4 units away from the axis of symmetry. So it's going to have a reflection 4 units away on the other side, right about here. So I'll go ahead and one more time. I'm like a measure twice cut once kind of thing. And there we go. There's my quadratic function. Now I'm going to go ahead and type it in just to make sure that we did everything right. So 3 times x minus 4 squared minus, minus 2. And there we go. It matches up. It matches up. Right. Now, Now let's say that we're trying to find the equation of a quadratic function. Well, as long as we know, what the vertex is, then we can, obviously we can find the value for a. Right. So, like for example, if I'm given 2 points, right? If I'm given a vertex, let's see. Let's say I'm given a vertex 3, 7, and let's say I'm given another point. So that's my vertex. And let's say I'm given another point that it passes through, like say 9, 4. Well, using the vertex form, all I have this would be my h and k. This would be my x and y. All I would need is to find the value of a to complete that vertex form. Okay, so if I substitute this for x and y and this for h and k, I can go ahead and find that equation. So that is, let's see, so 4, that's the y value, equals a times 9 minus 3 squared plus 7. So 9 minus 3 is 6. 6 squared is 36. So that's 36a plus 7. Subtract 7 on both sides. 36a equals -3. Divide both sides by 36. Reduce that fraction. My a ends up being -1/12. So the vertex form for this problem would be y equals a, -1/12, times x minus h, x minus 3 squared, plus k, which would be 7. So if you know your vertex and another point, you can plug it into the vertex form plug in the vertex form to find the value for a, and then put a back into your standard vertex form. Now we can also graph quadratic functions using function transformations. And again, here's the parent function x squared. Here's the axis of symmetry. Here's the vertex. Okay, and then I can, again, the minus h represents the horizontal translations. The plus k represents the vertical translations, and a represents x-axis reflections and dilations. And like I said, because the value of a determines whether the function opens up or down. Okay, so for example, if I wanted to do x squared minus 5 or x minus 4 squared, x squared minus 5, so that would be a vertical shift down 5 units from the origin, and then x minus 4 quantity squared would be a shift to the right 4 units. Okay, so let's go back to vertex form and standard form. So let's say I want to take my vertex form and expand on it. Well, if I expand on it, then I have change this to x minus h times itself. Then I would distribute. No, I wouldn't distribute. I would FOIL first. This is what I would get, and then I distribute the a, and then so now I have this. Now if I just said b to be equal to this part here and c to be equal to this part, then I have something to relate from a vertex form to a standard form. Okay, and there are techniques that we can use to still find vertex and axis of symmetry with the standard form. Like for example, if b is equal to -2 times a times h, and I solve for h, well, I just divide both sides by -2a. So here now that I solve for h, that right here is a way for me to calculate the x value of the vertex in standard form. Now, the only thing I would have to do from there is to plug in that value, to substitute that value to find the y value of the vertex. Now, the easiest thing to find on standard form is a y-intercept. Because if the x value is 0, then both of the terms with the x's will cancel, and I'm just left with c. So again, for standard form, the x value of the vertex is given by b over negative b over 2a, and of course that's also the value of the axis of symmetry. To find the y value of the vertex, you substitute this into the x for your from your function. And that's the y value. Here's the y value of the vertex, and the value of c gives you the y-intercept. Okay, so let's look at an example of that here. So let's say, let's annotate this real quick. So let's go ahead and try to graph a quadratic function in standard form. So let's say I'm trying to graph this function here. And the function that I want to graph is y equals 2x squared plus 8x minus 2. All right, so my axis of symmetry, the way that I'll do it is to do negative b over 2a, I'll make the b negative, or I'll change the sign for b and just do 2 times a in the denominator. Negative b over 2a, which is negative 8 over 2 times 2. That's negative 8 over 4, which is negative 2. So that's the x value of my vertex, along with my x value of the vertex. To find the y value, I'm going to take negative 2 and substitute it in here. 2 times negative 2 squared plus 8 times negative 2 minus 2. That's 2 times 4 squared. No, 2 times 4. I've already squared it. Minus 16 minus 2. This is 8 minus 18, which is negative 10. There is my vertex, negative 2, negative 10. And my y-intercept will be the point 0, negative 2. 0, -2. Let's try that on Desmos. Okay, so my axis of symmetry is the line y equals -2, which is about right here. No, -2, not +2. That's about right here. Sorry. My vertex is the point -2, -10, which is down here. My y-intercept is the point 0, -2, which is up here. So again, I'm going to connect those here. The y-intercept is 2 units away from the axis of symmetry, so I'm going to go 2 more units away on this side. And there we go. Now let's check it by putting it in here, 2x squared. Oops, wrong exponent. So minus 8x, oh sorry, plus 8x. Plus 8x minus 2. Of course, there we go. There's our quadratic function right there. And also, once we know the standard form, we can also convert these quadratic functions from standard form to vertex form. Let's use the previous example here. So, for example, our vertex was -2, -10. Our y-intercept was the point 0, -2. So if I put that into the vertex form, y equals, so -2 equals a times x minus h, so 0 minus -2, plus, or should be minus 10. Oh, gotta make sure to square. Let's see, 0 minus -2 is 0 plus 2, which is 2. 2 squared is 4, so 4a minus 10. Add 10 to both sides. 4a equals 8. Divide by 4. A is 2. And of course, well, actually, you know what? To be honest, I didn't need to find the value of a because it was already given. It was already given as 2. But anyways, that's why the value for a is 2. So my vertex form will be y. So this is my standard form, 2x squared plus 8x minus 2. My vertex form is y equals 2 times x plus 2 squared minus 10. Those would be the same thing. And it turns out we can actually use quadratic functions and parabolas to interpret real-life scenarios through word problems, but we'll cover a little bit more of that into the next section.